Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to Instrumentation and Measurement. This is lecture number 3. Today we will explore more static characteristics of measurement systems. Specifically, we will study about the sensitivity, the very important environmental effects, hysteresis, resolution, wear and aging, and error bands. In the last lecture, we studied from range up to nonlinearity. So today we will focus on sensitivity and environmental effects, hysteresis, resolution, wear and aging, and the error bands. Sensitivity. Sensitivity is the change in the output for unit change in the input. That is, it is the ratio. In the limit that delta I, that is the input, tends to 0, that is, for example, if we are looking at very small input change, this ratio delta O divided by delta I tends to the derivative, and this differential is basically the slope or the rate of change of output O with respect to input I. For a linear element, this dO by di is equal to the slope or the gradient k, which is constant throughout the line. But for nonlinear element, this differential is basically equals to k plus dn by di. That is, the sensitivity is the slope of the gradient, slope or the gradient of the output versus the input characteristics. Notice that the nonlinearity is the main element that will change the sensitivity of the element as the input changes. This is an example of sensitivity of a thermocouple. The electromotive force versus the temperature characteristics of a type T thermocouple is shown here. In this figure, we can see that the sensitivity evaluated at 100 degrees is approximately 35 microvolts per degree centigrade. For example, it means that at 100 degrees centigrade, if a temperature change of 1 degree happens, for example, if it becomes 101 degrees, so the sensitivity or output voltage will change for up to 35 microvolts. But at 200 degrees centigrade, the sensitivity is 42 microvolts. So it means that at 200 degree centigrade, a change of 1 degree plus or minus will cause a change in 42 microvolts in the output voltage. Let's do an example. Find the sensitivity of the thermocouple with the mathematical model, this one, 38.74 T plus 0.033 T square plus 0.000207 T cube. At T equals to 50 degrees, 150 degrees and 250 degrees. As expected before, so the sensitivity will be different at all these 3 points. The solution goes like this. Since the sensitivity is the rate of change, therefore the differentiate the system equation. We differentiate and arrive to this value, 38.74 plus 0.0664 T plus 0.000621 T square. Evaluate this differential at 50 degrees. We arrive to 43.61 microvolts per degree centigrade. Evaluate, now substitute the T equals to 150 degrees in the differential equation. We will arrive to 62.767 microvolts per degree centigrade, and at 250 degrees centigrade the sensitivity is calculated as 94.15 microvolts. Notice that how the sensitivity changed from 43.61 microvolts per degree centigrade to 94.15 microvolts per degree centigrade. This is how a nonlinear element changes its sensitivity. Now we will discuss about the environmental effects. In general, the output depends not only on the signal input but on the environmental inputs such as the ambient temperature, the atmospheric pressure, relative humidity, and the supply voltage, for example. Therefore, a graph or table given in the data sheet of a device labels the data is generated at a standard test condition, for example, at 25 degrees centigrade. So if this equation, which says that the actual output of the element is equals to Ki plus A plus the nonlinearity, is adequately adequately represents the behavior of the element under the standard environmental conditions. For example, the temperature was 200 degrees centigrade, 100 milli, 1 bar atmospheric pressure, 50% relative humidity, and the supply voltage was 10 volts when you operated that device. Then what will be the equation if there is any change in the standard environment? For example, the 20 degrees changes to, let's say, 30 degrees centigrade, and the supply voltage fluctuates to, let's say, 9 volts or 11 or 12 volts. So in that case, this equation is not able to capture any of the changes in the environment. There is no entry from or the relationship of the output with respect to this. So we need to have more detailed mathematical model to incorporate the changes due to the deviation in standard environmental conditions. So for that purpose, to develop the detailed model, let's explore the possible environmental inputs first. There will be some environmental inputs which will modify the linear sensitivity. Okay, so they will change the trend, and there will be some interfering inputs from the environment. They will interfere and they will actually change the straight line intercept or cause the zero bias. It means that the modifying input now, which is labeled as IM, will change the sensitivity. So if K is the sensitivity at standard conditions, when IM equals to 0, remember that the modifying input is basically the deviation. So IM is basically the deviation. If the input is changed from the standard value, then IM is the deviation from the standard conditions. So it means that the new value minus the standard value. What does it mean is, assume in the last case we say that the ambient temperature was, the standard value was 20 degrees, right? So if the temperature becomes, new temperature is 30 degrees, so the IM value will be equals to, the IM will equals to 10. Okay, so if they, so this is, be careful about this, that IM is not, there is no delta with the IM, but IM is basically the deviation or the difference between the current value, the new value, and the standard value on which it's available. Continue. The modifying input, so what happens is the K is now changed, K plus Km IM. Now we have a new Km is basically the sensitivity change, per unit change with respect to the IM. Similarly, so the modifying input is like this. If at ambient temperature at 20 degrees IM equals to 0, so at 10 degrees you subtract the new value 10 minus 20, so the new value will be minus 10, and the sensitivity will become K equals to 10 km. And if the temperature becomes 30 degrees and the standard value was 20, so the new value is 30. 30 minus 20 will give us the value of 10. So IM is 10. Notice that if when we talk about this model, actually here also we have this value of IM. Here we also have the value of IM that we have here. IM and the Km. Okay, so it's also here, but you see the value of IM here is actually 0, and because of this reason Km was not 0, IM was 0 here. That's why we were writing only sensitivity equals to K. So in a detailed model just like this one, you see how the modifying input is changing. It is changing the trend. So modifying effect because of the ambient temperature on a linear element. The second is the interfering input, which causes the straight line intercept to or zero bias to change. So A is the zero bias at the standard conditions when I equals to 0, and if the input is changed from standard value, then II is the deviation from the standard condition. Again, this, it is the difference, the new value minus the standard value. So coming back here again in the graph, so the A will be changed to A plus Ki II, where Ki is the change in the zero bias for the unit change in the II. If you see that if in let's say 20 degrees is the standard, this is the line, A is here. So if at a decrease in 10 degrees, it goes to down, so your the A will be changed to A minus 10 times Ki, and the value of II will be equals to minus 10. Why? Because the new value is 10. When you subtract 10 minus 20, we arrive to minus 10, and the new value is 30 here for the above line. 30 minus 20 will give us the 10, and the new value is the zero bias is changed, A plus 10 Ki, and here the zero bias is A minus 10 Ki. I have provided this referencing from the Bentley, and also written the page numbers so that you can easily refer back to the book. So now let's discuss about the coupling constants. We just saw Km and Ki, which are referred as the environmental coupling constants or the sensitivities. Notice that these sensitivities are with respect to the other inputs, which is, for example, the from II or Im. For example, Ki is the sensitivity with respect to II, and Km is the sensitivity with respect to Im. So the equation will be modified, and how it will be modified? The K will be changed to this value, new value, and A will be changed to A plus Ki and II. This is not Ki. There is I should replace this. I don't think so. This is yeah, it's wrong. So this is K will become like K plus Km Im times I. So we get a new model here. You see the model is now extended, and we have these two terms which are taking care of the environmental inputs. This equation 2.9 is basically can take care of this model and this model as well. Example of modifying input is, for example, the variation in the supply voltage of the potential voltage displays. So if the supply is varied, so there it will become Vs plus delta Vs. Okay, and the example of interfering input is, for example, for the reference junction temperature that we will cover in for the thermocouple in the next few lectures. We will come back to these concepts and do some practical or real design problems. Now moving forward to hysteresis. By definition, the hysteresis is for a given value of I. For example, for the given value of I, let's say at 10 degrees or so, the output may be different. Like for the same input A or I in let's say here, assume that this is some value, let's say this is 10. So for 10, if I go and check the graph, so it may be giving me this value. This is, let's say, 3, and while you are going up, but when it reaches to, let's say, 20, a value of 20, and then the graph is decreasing. While it is decreasing, it took a different path, and when it arrived back to the same point, the value of 10, you have a value different from this may be, let's say, 6. So you see, for the same input we have two different values, and it all depends upon the history. It all depends upon whether the input was increasing or it was decreasing, right? So this is how we define hysteresis, and it's a very practical thing that you see in different devices. We see the input here again, just like the nonlinearity, the hysteresis is also a function of input. So when we plot this alone as a function of the input, we see that it goes reaches a maximum value and then goes down to 0. So there is all again h hat here, and we can quantify it just similar to the nonlinearity, that finding out the maximum of the hysteresis when it reaches its maximum value, and then divide by the output span. Another example of hysteresis is, for example, a simple gauge system which converting the linear movement into the angular rotation provides a good example of hysteresis here. And due to the backlash or play between the gears, we can see that the x, for a given value of x, we will have a different value of the angle. Okay. Resolution is next. Some elements are characterized by the output increasing in a series of discrete steps or jumps in response to a continuous input increase in the input. So for example, what does it mean is, if you notice here, for this whole bunch, okay, let's say we are here on this spot, and this spot, this is the value, let's say this is some value 2. At 2, I have the system output reaches to, let's say, a value of 6. Okay, and then value moves to the next value, which is 3, 4, 5, 6, and let's say this value is up to, let's say, 5, and up to this value your output is not changed. It's still the output is 6. It was 6, it was a 6 again, and it was still 6, it was still 6. So there is a portion of input for which the output is not changing. So this minimum step that is needed so that the output will change, delta IR, this defines the resolution. So resolution is defined as the largest change in input that can occur without any corresponding change in output. So this value will be the resolution of this element. And this is an example of resolution. Okay, so expressed as a percentage of full scale deflection. So what was the maximum change in the input that will cause a little change in output, divided by the input. Since this is the input, we will not divide this by the output as we did for the nonlinearity and the hysteresis, because those are the you can say the parameters of the output. But resolution is like an input, it is on the input side. So here you see this is the an example in which sort of a potentiometer, it will move. We can see easily that there is a gap between these wires, and this defines the resolution of this potentiometer. Here it is, I draw them on paper. Wire 1 potentiometer here, for example, the x changes continuously, x will keep changing, but the x will keep changing here linearly, but the resistance will change in steps. It will like jump. There will be some there will be a little jump here, no value, or the previous value will be remaining the same, and then it goes to the next value jump. So one step equals to around one single turn of the coil, and if we have a total number of turns like 100, so the resolution will be like 1 by 100 times this. So this will be a resolution of 1% in this case. And the resolution of ADC, we will come back to this in detail with the ADCs and the other data acquisition hardware in use in the last part, the fourth part of this course. In simple terms, the output of the ADC changes in steps while the input is continuously changing. So thus the resolution is the change in the output required to cause the output code to change by the least significant bit. Just to provide a definition here. Wear and aging can cause the characteristics of an element, for example K and A, to change slowly but systematically throughout its life. Now again, we are talking about the sensitivity of the element and the bias. It will change throughout the life gradually. So for example, this is an example of a spring constant. A spring constant equals to K naught minus BT. K naught is the initial stiffness and B is a constant. And with the passage of time, the stiffness KT will change. Okay, so the more time it will be changing because of here. Constants of thermocouple, for example, measuring the temperature of a gas leaving a cracking furnace, changing, it also changes systematically due to the time. The constants that I'm referring here uh, is an example of, let me remind, uh, yeah, here. So these are the constants. You see, these are the constants. They will change after, for example, with some current data, you have to perform some kind of regression to calculate, validate that these are valid, still valid. They are not, these constants are not, these coefficients are not changed. So these are the constants. With the current data, we have to make sure they are same. So yeah, so wear and aging is also basically can change the and it is because of the chemical changes in the thermocouple installed wherever you have installed it there. The last thing is about the error bands. Error bands. Now imagine that the nonlinearity, the hysteresis, the resolution effects in all the modern sensors and transducers, and sometimes they are very small, but they are there, and it becomes very difficult to model them. They are not much, but they are there, and collectively they can be significant. Uh, but it might be difficult sometimes to quantify them. So the easiest way to tell about the deviation is manufacturers will define the performance of element in terms of error bands. Error bands are what? For example, this is again the deviation. This is the straight line that we require, and this is a kind of the maximum deviation. So what they have done is going back, and I would like to, like for example here. So what someone has done is let's say, yeah. So if, for example, if I draw this line here and here, okay, and ideally it should be continuous line, okay. So if it is not a continuous line, and I get this idea about that, okay, this is the maximum that it will vary, okay, here. So this is what we just draw a line that the steps will be for the resolution. For example, they will be coming like this one, okay, they will be coming like this. These I'm trying to make these small steps here, okay, like this resolution. So resolution can be defined it here. Similarly, the nonlinearity may be drawn like this. It goes to the maximum and then come back here, and also the hysteresis can also be, if you see, I'm drawing for the hysteresis as well, okay. So within this band we can so this can be like a it's going up and then it's going down, hysteresis or the nonlinearity. So all of these, if it is difficult to define nonlinearity, hysteresis or resolution effects, but they are here, the manufacturers can use a band, error band, and for example they can just tell us that whatever the value is, expect that it may have a plus minus h variation from the straight line, and this variation is okay. So this variation is coming to this point. This variation is basically quantified by the mathematical terms, but there is another way of quantifying or representing this mathematical variation. What is that one? That is, we use, for example, another function is from statistics, which is called probability density function, and there are different type of probability density functions. For example, if the variation is following this normal distribution, it can be a triangular, log normal, uniform, or this is also called square, beta, and there are so many. So this variation which was basically well defined by nonlinearity, hysteresis and resolution, we also have this another way of defining this. If they don't exactly be quantified by nonlinearity, hysteresis or resolution, we can use we can try to find a better function based on the data, probability density function. And what basically probability density function is, it is defined so that the integral is the probability, this is the probability of x lying between x1 and x2. So basically this is how, and also in the measurements what we are saying is within this band it will be having. So if you come here, this is the area that we are mentioning, that at this point the value the output value will be output or input value, the value of the variable that we are trying to represent the variation in will be within this limit. Okay, so this is the again so this probability of this x from x1 to x2, so this is the probability that x will lie between x1 and x2. This is the function. And in this case, rectangular probability, for example, for this error band, the rectangular probability function is the best one to represent. There are many probability density functions. One of them is rectangular. So when you represent this variation or try to, it's like we are trying to model our variation with this by using the error band. So the formula for that one will be for the error band will be, it will go like this one, having the width of 2h and height of 1 upon 2h, and the mathematical model will be like this, that with the ideal plus minus h, it will be it will be 1 upon 2h, and above ideal plus h will be 0, and above ideal minus h it will also be 0. Note that the area of the rectangular is equal to unity, because this is probability, and this is the probability of O output lying between this ideal minus and ideal plus. Okay, thank you very much. For any questions you can contact me, write me through these emails.